Alright, we're getting right back into section 7.4 on vector still. We're bringing in the idea of the different things that can happen with applications, and that's what we're working towards. First things first though, when you're dealing with applications, most times you're best off working in component form. So this, I don't know if I would say this is a statement or some kind of a theorem that indicates a little bit about exactly how we're going to need to set this up to be able to do some of these story problems having to do with magnitude, direction, and components of a vector. If we let vector v be AB, that's component form, a vector in standard position. See, there's vector v right here in standard position. Notice that its initial point is at the origin. And let's see on that the angle here, the direction angle here is theta. So let's say, and let theta be between 0 and 360 degrees, be the direction of vector v measured counterclockwise positive from the positive direction of the horizontal axis or the positive x-axis. So we know that the magnitude is equal to the square root of a squared plus b squared, and we also know from before that the tangent of this angle is equal to b over a and b being the components. But now what we're going to do is we're going to go a step further. Since a is this component here, if I set up my right triangle, and I'm going to try to drop this down. So I have my right triangle there. We can use SOHCAHTOA to come up with the fact that a is going to be equal to the magnitude. Now the magnitude would be this distance right here of the hypotenuse times the cosine of theta, and that b, which would be the vertical component, would be equal to the magnitude times the sine of theta. And that means that if we think of the vector AB in component form written with the unit vectors I and j, then we can plug in for a and b, and we can write it in this form. And believe it or not, this is the way that we want to go. So we're going to put a little star next to this guy here so that we'll remember. Alright, now this is just kind of setting up a story problem. It's not a true story problem. It's just kind of setting it up. It says a man exerts a force of 80 pounds on an object by pulling on a rope at an angle of 30 degrees from the horizontal. And we're going to write a force vector that's going to represent this in terms of I and j up here. So I've drawn a picture. This is the weight, and this is the rope, and those are supposed to be hands pulling at the rope, and this is going to be to the horizontal, and we have an angle of 30 degrees. Now I know it's not perfectly 30 degrees. Looks like it's a little smaller than that, but then I just kind of eyeballed it there best I could. Now what I want to do here is I want to make note first off that the magnitude of this vector is 80 pounds. That part's given. This is a force vector, that's why I'm using a capital F here. And we also want to be able to write that the vector itself, which I'm going to call vector F, is equal to the magnitude times, oops, I got to get the magnitude, 80 times the cosine of our angle here, which is 30 degrees, I, plus the magnitude, the sine of 30 degrees, j, vector j. Well, the sine, excuse me, let's try that again. The cosine of 30 degrees is the square root of 3 over 2. So this is 80 times the square root of 3 over 2 times vector I, and 80. Now the sine of 30 degrees is 1/2 times vector j. So I'm going to simplify a little bit. And I have 40 square roots of 3 times I, which I'm going to write as 40. I know it's okay to write the square root of 3 and then the I, but sometimes it's just a little tough to tell. Sometimes I'll put the I there, but most of the time that I put I there, I'm talking about I being an imaginary number. And in this case, it's a vector, and that vector symbol above it should be enough for us to kind of keep it clear. So I'm going to go ahead and write 40 square roots of 3 and then vector I. You can definitely tell it's not under the radical. And then half of 80, of course, is 40. So this is 40 times vector j. And this is my force vector of the hands pulling the object with a force of 80 pounds. Okay. Now the next example I have has to do with throwing a ball. A ball is thrown from a height of 1 meter. So here's our guy that's throwing the ball. He lets go of it 1 meter above the ground. And at the time of the release, the velocity of the ball, now the velocity is of course a vector, is given by 27.2 I plus 12.7 J, where each component is given in meters per second. Alright, we're going to find the initial velocity, v sub 0, and the angle, theta, above the horizontal in degrees. So this would be theta. Okay? At which the ball was thrown, and we'll round our answer to 1 decimal place. Well, in this case, the way this is set up, this guy right here would be the horizontal, this would be 27.2. This guy right here would be the vertical, and this would be 12.7. So that would be the A and the B that we'll need, and we're going to go ahead and take that, and we're going to find the initial velocity, in this case v sub 0, which would be the magnitude of vector v. So this would be the square root of 27.2 squared plus 12.7 squared. And of course, I didn't bring a calculator with me. I seem like I always forget to bring the calculator when it's most important. This turns out to be 901.13, 901.13, the square root of that, which would be about 30. And so to approximate this, I would go to, let's say, a couple decimal places here. 30.019, 30.019, and this would be in meters per second. So that's the initial velocity based on this, of it going in this direction here. We're going out this way at this angle of theta. Now, to actually find the angle of theta, I'm going to use the fact that the tangent of theta is equal to opposite over adjacent, so that's 12.7 divided by 27.2, and so theta is going to be equal to the inverse tan of 12.7 over 27.2, 127 over 272, and again, I don't have my calculator, but I've written it down somewhere. Here it is, 25.028. 25.028, and this is in degrees. Now, what do we want? We want the initial velocity, v sub 0, and we want the angle, theta, and we want this rounded to 1 decimal place. So in this case, the ball was thrown at an initial velocity v sub 0 of, to the nearest tenth, 30.0. I've noticed some students, when they round it to the nearest tenth, if it turns out to be 30.0, they don't put down the 0.0. Yeah, you do, because it's to indicate that you're rounding it to the nearest tenth, so you would need that, even though we know that that's not really adding anything to the overall number. It is showing the precision, or where you've rounded to, and this would be in meters per second, at an angle. And let's see, how's this problem stated? Above the horizontal, I guess I could say something like that. What was it? Of 25, oh, let's try that again. 25, here's another 0.0. I can get this decimal point in there. Degrees above the horizontal. Remember, if it's a story problem, you probably need to write it out. Now here they ask for just a particular force vector, so that was stated. But here they're talking about an actual story problem. If you want to here, it probably wouldn't be the world's worst thing to write it out in a short sentence, but I'm just going to kind of leave that one in there. It's status quo. All right, now, for me to do this story problem over here, I want to bring in the idea of what's going on in the problem. Okay, so we're going to consider an application where a plane traveling with a velocity vector p for plane, relative to still air, the plane encounters a current, wind current, vector w, which w for wind, that alters its course, and the resulting vector r for resulting of the plane, is given by r equals, vector r is equal to vector p plus vector w. You see how the two forces act upon the plane by taking the resultant or by adding the two vectors. Now, we're going to have to go component form on this, but I just want you to think about this common sense wise. If you're not necessarily in a plane, let's say you're just jogging down the road and it's windy and the wind's blowing in your face, you know how that affects you. If the wind's blowing behind you, you know how that affects you. It slows you down or it speeds you up. If the vector is blowing at an angle, you might, depending on how strong the wind is, you might have to compensate for that by the way you run by an emphasis to one side so that you run straight or run on your path. So this is what's going on here. We have a plane. The wind is blowing. It's going to affect it. It might affect it head on or as a tailwind, or it might be striking it as an angle, but that's going to affect it. And that, of course, affects the pilot of the plane because he's got to compensate for that wind so that he flies the flight and goes the path that he wants. So in this case, we have a plane traveling with an airspeed of 400 knots at a bearing of south 20 degrees east, and it encounters a wind of 50 knots acting in the direction of south 30 degrees west. Now, 400 knots and 50 knots are going to be the vector p and vector w's magnitudes. We're going to round to the nearest whole unit on these. So really, to get a good idea of what's going on, you probably want to make a sketch. So to do that, I used up so much space, I'm just going to go ahead and kind of erase some of this. Certainly I hope I don't mess up my video and have to start all over again, because I will have to do a lot of writing to make up for what I just erased. So in this case, let's set that up here. We're going south and east, so I want more space on this side here. So let's go north-south right here. Oop, this be north. Hopefully that's straight enough. And let's go up here. And hopefully that'll be enough for what we need to get going. East and west, right. So in this case we have 400 knots, 20 degrees south, 20 east. So I'm going to approximate this, and I'm going to make 50 knots worth 2 inches here. So that's going to be 16. So I'm going to approximate 20 degrees. It could be about like this. And let's see, 2, 4, 6, 8, 10, 12, 14, 16. So here's our plane. This is 400 knots. And this angle right here is 20 degrees. Hopefully you can see that as I was standing right in front of it. Now there's the plane. It encounters a wind of 50 knots acting in the direction of south 30 west, so it's kind of going this way. So I am going to set up, or try to, another set of axes here for north, south, east, west. I'll make these dotted, at least I'll try to. Okay, and this time it's 50 knots, so based on how I drew this, that's going to be worth 2 inches as far as this ruler is concerned, and I need south 30 west, so south 30 west. So let's see, approximate this, that's maybe too much. That could be about 30. And that's this guy right here. Now this was, well, we didn't give it a name. This would be vector P, this is the plane here. And this would be vector W, as that's the wind that's blowing on it. Now, the resultant of this is, I've erased it, but it turns out that the resultant R was the sum of the two vectors, so geometrically, let's do it this way. So the wind's kind of behind it, but it's off to the side a little bit. So it's going to kind of speed up the plane, but also it's going to alter the course here. So we're going to try to draw that. There it is. And this is what's happening. This is vector R. Now, to go about and to find what I have drawn out here, don't get out quite that far, just in case I need a little extra space. All right, vector P is going to be the, this is the, gosh, I'm sorry, I'm stammering here. This is the magnitude, and this is my direction. So vector P is going to be the magnitude of vector P here, let's see, times the cosine of the angle. Now, what angle am I dealing with? Since it's this angle here and this is 20, that angle is 290. Yikes. So this is going to be the cosine of 290 degrees I plus the magnitude of vector P times the sine of 290 degrees times vector J. Oops, vector J. Hopefully you can see that okay. Now again, this would be a really good time to have a calculator. And of course I didn't bring one. Silly me. So this is going to be 400 here. The cosine of 290 degrees I plus 400 the sine of 290 degrees plus or times vector J. So I've done this on a piece of paper from before. I wish I had my calculator with me though. This is going to be approximately 136.8 I, actually minus, because it's going to be negative in the fourth quadrant, minus 375.9 times vector J, and I think they asked for it rounded to the nearest whole unit, so this is going to be even more of an approximate. This would be 137I minus 376J, and that would be the plane described by vector P, by what we call vector P here. Now in the second part it wants the wind, so it's very similar. The wind vector is going to be the magnitude of this vector times the cosine. Now in this case the angle for the wind, remember this is 30 degrees here. So what we're looking at is 180 and 60 more, that'd be 240 degrees. At least I can do that one in my head. I plus the magnitude of the sine. I'm sorry, I'm probably right in front of the camera so you can't see what I'm writing down. Don't forget your symbols, those are vectors. The cosine of 240 is negative 1/2, and this is 50. So I'm going to get 50 times negative 1/2 I plus 50. Now the sine of 240 degrees is negative square root of 3 over 2 vector J. So this is negative 50I minus 50 square roots of 3 vector J. Now they wanted it to the nearest whole unit, so this is okay. But vector W is equal to negative 50 times vector I. Remember that's 1, 0 in component form. And then this turns out to be 50 times about 1.732. Or actually, hang on a second. 50 times negative 1/2 is 25. Almost messed that one up royally. And this is 25 because I forgot to take half of it. So 25 times the square root of 3, which is about 1.732, turns out to be about, if I'm not mistaken, about 43. This is 25 again. Good Lord, all this work and I'm going to mess up now. Times vector J. I think it's 43. I'm going to have to check my calculations. It is. Now, to find the true speed of this guy, well, what I'm going to need to do here is I'm going to need to set this up so that the the magnitude, well, hang on a second, one thing at a time here. So this is going to be vector r is equal to vector p plus vector w. All right, so if that's the case, then I'm going to get 137I minus 376J plus W, which is negative 25I, and I'll go ahead and write minus 43 times vector J. So this turns out to be 112 times vector I minus 80 times vector J. So if I want the magnitude of vector R, this would be equal to the square root of 112 squared plus negative 80 squared. So again, that's an approximate, but this is going to turn out to be 433.7, or in our case, what we need to the nearest whole number, this is going to be 434 knots. And that makes sense if you think about it, because the plane's going 400 knots, the wind is kind of pushing it a little bit along, so it should be higher than 400 knots, and that's exactly what happens. Now, to find the actual bearing of the plane, I would need to find this angle right here. Okay, now, to do that, let's see, probably have to do the tangent of this angle being B over A, so that would be, I gotta find my spot, negative 80 over 112. Well, hang on a second, do I have the right one? Well, I can't add. I thought that was 37 and 40. I thought that was a small number. That's, sorry about that. Here we go again. That's a 9. That is 419. So this was 419. I was wondering why that number looks so weird, because I didn't think they would add up to be that much. 419 negative squared, which is this. Whoa, almost messed that one up beyond repair there. But I do get 434 knots. It's just that it's not negative 80. It's going to be negative 419. Now remember, our angle is going to be like this, and we need this part right here for our measure. So what we're going to do here is we're going to take the inverse tan. The inverse tan of this angle, it turns out to be negative 75.03 degrees. So what they're doing here is they're doing this. I want this. So I need 90 degrees minus, and if we round it to the nearest whole number, minus 75 degrees. So the bearing is south 15 degrees east. So the bearing of the plane is south 15 degrees east. And what else did it say? Find the true speed. And the plane's true speed is 434 knots. Now, it's what happens when you don't bring a calculator. You depend on your memory, and you depend on looking off a piece of paper to write these numbers down. And I made all sorts of little silly mistakes here. Forgot to multiply by 2 and such, or divide by 2. But this is how it goes about to do it, and this is how you find the resultant of these two vectors acting on the plane. The plane itself, and its velocity and its direction, as well as the wind blowing on it, the air current. So we can do this with boat and with water current as well. But we are going to have to make sure that we write our vectors in this form and then work from there as far as if we're adding the vectors together as we did in this last example.